So the last thing that we're going to learn in this class is how to use everything that we've been working on in Chapter 4 on exponential and logarithmic functions to try and solve some real-world problems. So let's start with some financial models. A lot of financial systems rely on compounding interest. And to see what that means, we're going to actually look at a concrete example. So suppose you invest $1,000 in a savings account and that account earns 1% interest annually. If your interest is just calculated at the end of the year, so they wait until the end of the year and they give you the 1% interest on that account, well, bear in mind that 1% written as a decimal would be 0.01. You just move the decimal place over 2 spots to the left. And so we can calculate this by starting with your initial investment, 1,000, and then adding what you earn on interest, which would be 0.01 times 1,000. Since we have 1,000 in both of these, it makes more sense to factor that 1,000 out in front and rewrite it as 1 plus 0.01. So it's $1,000 times 1 plus 0.01, or $1,000 times 1.01. All right, and in the end, what you end up making there is, well, this part here, your interest ends up being $10. So in the end, you get $1,010. All right, but usually banks don't actually calculate the interest this way at the end of the year. Instead, what they do is they calculate the interest many times along the way. So to give you an example, if the interest compounds monthly, what that means is that your 1% annual interest rate gets divided up among the 12 months of the year. So you'd really earn 1/12% each month. And it might seem like that doesn't make a difference, but it does at least a little bit make a difference, because what happens is after your first month, you get that extra 1/12% of interest, so that after month 1, you have $1,000 and an extra 83 cents in your account. Right? That's from your extra 1/12% of interest that you've earned. And now, during your second month, you're not just going to be earning interest on your original investment, you'll also be earning interest on that extra 83 cents you just earned. And again, it's not going to be a lot of a difference, but it is going to make some difference, right? So after the end of the second month, they're going to do this again. They're going to take what you have now, which is $1,000.83, and they're going to give you 1/12% interest of that. And now, at the end of the second month, you have $1,001.66. All right, we keep repeating this process, and what you're earning is going to grow sort of exponentially here. So repeating this process means that you can figure out how much you're going to get in the end by starting with your initial investment of 1,000 and multiplying that by 1 plus your 0.01 interest rate divided by 12 raised to the 12th power. And in the end, the amount that you earn is going to be this right here, $1,010.05. Ooh, wow. You earned an extra 5 cents over what you had earned if it had only compounded once at the end of the year. Okay, so it's not really a huge difference, but on a larger scale, it makes more of a significant difference. So to give you an example, let's say we started with a bigger investment of $10,000, and instead of just investing it for a year, we kept it invested for 30 years. This is going to make a substantial difference. It's exponential growth in both cases, but in the simple interest case, where it's only annually that it adds interest, only once at the end of the year, you can compute how much you'll have at the end of 30 years by taking that $10,000 initial investment and multiplying it by 1 plus 0.01. 0.01, that's your 1% interest rate. Right, remember, 1% interest rate corresponds to the decimal 0.01. Raised to the 30th power, because it's 30 times that this interest is going to compound. And you end up with $13,478.49. But if you compound monthly, if you divide up that 1% interest over the 12 months of the year and you compound it 12 times, then over your 30 years, you're going to earn that $10,000 times 1 plus your interest rate divided by 12 months, raised instead of just to the 30th power, raised to the 12 times 30th power, because there's 12 times 30 months over the course of those 30 years. And so in this case, you're going to earn $13,496.90. So in this scenario, you end up earning an extra almost $20 over the course of these 30 years. And again, that doesn't seem like a huge difference, but given the fact that it's the exact same initial investment and the exact same interest rate, you can see why it does actually make a difference how often this interest is compounding. And in fact, the more often it compounds, the more money you're going to make. So, for example, you could get a bank account that has daily compounding interest. And in this case, the amount of money in your account is going to be found using the formula A is your future amount, P is your initial investment, however much you put in at the beginning, R is your interest rate as a decimal, and T is the number of years that you're going to invest the money. And so we have that in this example that we saw before, if you want to know how much you'll have in the future, you take your initial investment of $10,000 and then multiply that by 1 plus the interest rate, that's 0.01, divided by 365, because there's 365 days in a year, and raise that to the power of 365 times the number of years. I think in the last example we did 30 years. And what you end up getting then is 13,498.53. I just put this into a calculator because there's no way I can actually compute this. Let's go back for a second. Okay, with compounding monthly, we had 13,496. Now we have 13,498. So we got an extra $2 by compounding daily. It's not going to go on forever, right? You can sort of imagine, well, what if it compounded every second? What if it compounded every half a second? But it eventually is going to reach a limit. And that limit is what we call continuous compound interest. The most that you could compound is continuously. So not just every second, but if you can imagine it compounding every possible moment of time, then you end up with this formula for figuring out how much you've earned in the end. A is equal to P times E to the RT, where P is your initial investment, T is the number of time that you've invested in years, and E is the constant that we've discussed before, that 2.718. So in the same example, the interest that we would earn if we compounded continuously would be given by the formula 10,000, that's your initial investment, times that constant number E, raised to R, that's 0.01, that's your interest rate as a decimal, times T, where T is the number of years, 30. Or you could write that as 10,000 times E raised to the 0.3. And plugging that into a calculator, I end up with $13,498.59. Okay. How much was that over the last one? Almost nothing. It's just a few cents more. And so the most you can possibly earn through compounding interest is through continuous compound interest. And a lot of banks do compute their interest rates that way. Okay. Now, let's look at a couple of examples. How much should you invest in an account that's earning 2% annual interest compounded continuously if you wish to have $10,000 in 5 years? All right, remember, with continuous compound interest, we're working with this formula here. A is equal to P times E to the RT. A is the amount that you're going to have in the future after the interest has been accumulating. So we want to have $1,000 in 5 years, so that $1,000 is our future amount. So we're going to let A be equal to 1,000. We also know that the time involved is 5 years, because they told us that here, and the interest rate involved is 2%. So as a decimal, that would be 0.02. Filling all of this in, we get 1,000 is equal to P times E raised to the RT. E raised to the 0.02 times 5. That is 1,000 is equal to P times E to the, 0.02 times 5 would be 0.1. And so I can solve for P, right, solve for what your initial investment would need to be by dividing both sides by E raised to the 0.1 power. Again, I just plug this into a calculator, but that's going to give me that P is going to need to equal 904.84. In other words, you would need to invest $904.84 into this account if you want to have $1,000 in 5 years. That's not bad. You earned almost $100 in those 5 years. Okay, let's do another example. So suppose you have $5,000 to invest in an account. All right, that's what you have now. So that should be your initial investment. And it's earning 3% interest annually. I didn't mention it here, but I meant to mention it using continuous compound interest. So we'll be using the same formula here. Okay, so we're still using this formula A equals P times e to the RT. So our interest rate is 3%, so R would be 0.03. 3% as a decimal would be 0.03. How long would you need to invest that money? Ooh, we don't know that. We're looking for the time here. In order for your investment to double to $10,000. So they want to know how long should your amount of time be if you want to have $10,000 in the future. Okay. Sadly for us, a 3% interest rate just doesn't really happen anymore. Not in this economy, it doesn't. But we'll just pretend for now that that's a reasonable interest rate. All right, so we have that our future amount that we're trying to get to is $10,000. We can currently invest $5,000. And so filling everything into this formula, we have 10,000 is equal to 5,000 times e raised to the 0.03t. We don't know t yet. We're still trying to figure that out. So what we need to do is solve for t. T is stuck up in the exponent here. How do we solve for t if it's currently an exponent? Well, lucky for us, we just did an entire video on this. The last video was on solving exponential equations. We know how to do this. We can get that t out of the exponent by taking the natural log of both sides. But first, we need to get this term, e to the 0.03t, all by itself. So to get that term by itself, I want to get rid of the 5,000. It's being multiplied, so to get rid of it, I'm going to divide both sides by 5,000. Right? Now on the left-hand side, 10,000 divided by 5,000, that's just plain 2. So we have 2 is equal to e raised to the 0.03t. Now to solve this for t, I need to get that out of the exponent, so I need to do the inverse operation of e to the something. The inverse operation of e to the something would be log of something, or natural log of something. So I'm going to take ln of both sides. I can do this because of that one-to-one property we talked about in the last video. So we have ln of 2 is equal to ln of e to the 0.03t. Now the ln and the e cancel each other out. So we have ln of 2 is equal to 0.03t. And finally, to solve for t, just divide both sides by 0.03. I'm going to have to do this on a calculator. I don't know what this is off the top of my head. But plugging ln of 2 divided by 0.03 into a calculator, I get that my time is going to be equal to, let's see, I did this on a piece of scrap work somewhere, 23.1. Oof. That's in years. So you would have to wait 23 years for your investment to double. I guess it's not so bad. With an interest rate of only 1%, that would take a lot longer. Much longer. Longer than we probably have in our lifetimes, maybe. Okay, so you can see how using what we learned about solving exponential and logarithmic equations can come in handy here. Now let's do one more example that's not financial based. Let's talk about exponential decay, and we'll talk about population decay. So there's other applications to exponential and logarithmic functions that apply to population models. So for example, if you knew that a population of 1,000 people is decreasing by 3% each year, this is going to represent exponential decay. So now our interest rate is really negative 3% because your population is decreasing each year as opposed to increasing with an interest rate, right? And so we can figure out how many people will remain after some number of years using this formula. It's similar to the one that we originally did when we were compounding monthly or daily, or even annually. So Now we have our initial number of people on the outside, that's our 1,000 people, times 1 minus 0.03, subtracting because the population is going down, decreasing, raised to the 30 power because 30 years have gone by. And that means after 30 years, our population has gone down to 401, very small. Let's do another example. Let's say that the population of a large college is 20,000 currently, but it's decreasing at a rate of 1% each semester. All right, so our rate here of 1% would be 0.01, but it's decreasing, so it's really a negative 0.01 since it's going down. Not only that, but it's going down each semester, not just every year, but every semester you're losing another 1% of your population. So if there's 2 semesters every year, we want to figure out what the population will be after 10 years. Well, our population is going to be, let's call it A. That's the population in the future. It will be given by the current population of 20,000 times 1 minus the percentage decrease rate, 1 minus 0.01, raised to the power of how many times it's decreasing. Well, it's decreasing 1% every semester, so after 10 years, that means it's decreased 20 times, because there's 2 semesters per year, and we're doing this for 10 years. So our exponent here is actually going to be 20, because we've decreased the population twice a semester for 10 years. And again, this is something I'm going to have to compute with the calculator, but it'll be 20,000 times 0.9 to the 20th power. Plugging that in is going to give me 16,358. So 16,358 people after 20 years.